Pulkit has joined, or has he joined?
No, not yet. I don't see. Who?
Pulkit.
Ajayan.
Ajayan.
Yeah, he has not yet joined.
Okay.
It must be just very early in the morning for him. Is that
Sorry?
right?
Yeah,
It
sorry.
must be very early in the morning.
Yeah. The same time, no, the time yesterday what our friend had, it will be more or less same time, I think.
He is in Houston, no? So Houston maybe.
The time zone looks like Wisconsin and Houston more or less same time zone.
Oh, okay.
Maybe half an hour.
Yeah, half an hour. That's what I noticed. It is given as 7:30 instead of 7. So I thought this half an hour must be the time gap.
Yeah. He has joined. Hi.
Hi.
Hi, Ajayan. How are you?
Hello.
I think you are in muted condition. Hi.
Hey, how are you? Good morning.
Fine. How are you?
Houston. Hi, GVSS. How are you? Nice to see you.
Yeah, fine. Yeah. Nice seeing you.
Boy, it's been a while.
What's the time over there?
Yeah.
What is the time?
Here it's about 9 o'clock, right?
Okay.
9 o'clock. Oh, it's not
I
too
hope you have
inconvenient.
taken your breakfast.
Well, I mean, I'm going through intermittent fasting these days, so no breakfast.
Oh. I think you used to do that even
works
earlier.
pretty well for you, that intermittent.
It's working out well. Thank you. So today is the last day of this innovation, right?
Yes.
How is the family again? Purnima, your daughter?
Yeah, they're all fine, actually. My second daughter just graduated from high school.
Okay.
And she's going to Rice as an undergraduate.
I remember her only as Achi. I don't know her name.
Yeah. I mean, she is Ahi, second one.
Ahi, yeah. 2 years kid at that time.
So how are you? I mean, are you still in BHU, GVSS?
No. I'm right now at Kakinada.
Oh, yeah, right.
Close to Visakhapatnam. And after my tenure, then I spent 1 year at BHU as emeritus professor and 1 year at IIT Roped. Then I settled here.
So Kakinada is an NIT or what is it?
No, Kakinada is, I settled here just for...
your family is there.
Family. Yeah, family. There is one JNTU at Kakinada. It's one of the very early old-time engineering institution, and that got converted into JNTU, Jawaharlal Nehru Technological University, one of the 4. So that's where it is.
Yeah.
And how are you, Dr. Mukhopadhyay? It's been a while.
Yeah, sure, I'm fine. And we are actually looking forward to listen to your lecture because this is the last day. And yesterday there was our Dr. Pulickel Rohadgi. He is also
I know.
alumni of our department. So thank you very much that you have accepted our invitation. Yeah, you might know that Dr. Manna, no? Dr. R. Manna.
Yeah, right. I think I one of the meetings.
Yeah, last time we met. I think DCAM time you came here.
You were there also, Ismanam, right? Last year, Ismanam.
Yeah, this was in Murthy was organizing it, right?
Yeah. In Chennai.
So how are things, at BHU? COVID is now past, and are you?
Yeah, a few weeks back it was a really very bad time, and whole Varanasi was also undergoing a very horrible time. But right now it is under control. and still the students are not allowed to visit the campus.
Oh, I
So,
see. So you
yeah,
still don't have
online,
students on campus. I see.
yeah,
Yeah.
online classes going on, and we also kind of just lost three of our colleagues from the institute. One is from metallurgy, one of our Professor Indrajit Chakraborty.
Mm-hmm.
Due to COVID, just 14 June, he passed away.
Oh my God. I mean, I heard that Professor Owen Srivastav passed away.
Yeah.
That I
Yeah.
saw. Yeah.
So when Srivastava, his student, just 7 days back, he passed away.
Oh my God.
And his earlier PhD student who was in NPL Delhi, Dr. D.K. Misra, he also passed away.
Mm-hmm.
He was a scientist in NPL. This is
I see.
mainly because of corona-related issues.
Yeah. Yeah, here things are back to normal, actually.
Yeah.
A lot of people have been vaccinated, and people don't even wear masks anymore here.
Yeah.
So,
But in Varanasi, it was very severe. And in Andhra Pradesh also, this particular district where Kakinada is located is still having lockdown during the daytime. Up to 2 o'clock only we can move. And after that it is closed. And the cases are still not on the rise, but they are not even decreasing much. Not
yeah, I
possibly.
really hope that things will be better soon.
Yeah.
But this mask thing, still I'm not sure that in US I heard that because my daughter is there in Ohio State University, Columbus. She said that after 2 vaccines that we have been told that mask is not required.
Yeah,
So
I think the
I'm not very
CDC,
sure
right.
that Delta Plus and other variants when they are coming up, whether the mask is still not kind of.
Well, I mean, I think the CDC guideline is that the masks is not mandatory. It is recommended, but it's not mandatory. So, yeah, I mean, again,
Yeah.
I
There
think the
have been
idea is that
debates
the
about
vaccination gives you protection, right?
Yeah,
whether the
Delta
mask can
Plus.
really filter, whether the mask can really filter the virus, which is so small, also
That's the other
is
question, right?
debated. So,
Yeah.
Because today I heard that Delta Plus variants are also coming up in various places. And whether that variants, it seems that that is a much more dangerous in terms of the transmission kind of issues. And
Yeah.
it can transmit very fast.
but is Delta plus fungus or the variant of COVID
They
coronavirus?
claim that Delta Plus variants.
But some people say it is black fungus. Some are saying it is a variant. Not very clear.
But WHO, that announcement says that Delta Plus variants is communication point of view is very fast. But it could be related to black fungus. I'm not sure, but that's what is the kind of announcement is coming up.
Yeah.
Yeah, I think the time is.
It is the time. Yeah.
Yeah. So okay.
Shall
You can start.
we? Yeah. Let me introduce the speaker. It's really maybe on an informal way. It sounds funny to introduce Ajayan, who is already well known. I don't think there is any country left where he is not known. This is the reputation that he has earned for himself as an outstanding scientist. And also, we are very happy that he is associated with the department at various stages, starting from his graduation from our department. And the university during its centenary celebrations has ranked him amongst the top outstanding alumni that made a remarkable progress or significant contributions to the country as a whole and at the world scenario. He also has been interacting with the department, with the students, and several students had gone to him to work in his laboratories wherever he was. I would now give a formal introduction, as it is also required for the benefit of those who are freshers to this particular area. Professor Pulickel M. Ajayan, Benjamin M. and Mary Greenwood Anderson, Professor of Engineering, Department of Material Science and Engineering at Rice University. He has worked with Ijima way back when he was at NEC, and he solidified metals in carbon nanotubes. That is when the world turned their attention to him, and since then there is no stoppage, and he has become what he is now from that day onwards. Professor Ajayan is one of the pioneers in the field of carbon nanotubes. That's how they started, and has demonstrated several possibilities for using these quasi one-dimensional structures as templates and molds for fabricating nanowires, composites, and novel ceramic fibers. He earned his BTech in Metallurgical Engineering from the Indian Institute of Technology, Banaras Hindu University in 1985, and PhD in Material Science and Engineering from Northwestern University in 1989. After 3 years of postdoctoral experience at NEC Corporation in Japan, he spent 2 years as a research scientist at Laboratory of Solid-State Physics at Orsay in France, and nearly a year and a half as an Alexander von Humboldt Fellow at the Max Planck Institute for Metallforschung, Stuttgart in Germany. He has published a book and around 1,000 journal papers with nearly 95,000 citations and an index of 150. These figures must be changing every day. His awards include the Pierce Memorial Award by the Royal Society of Chemistry UK, Senior Humboldt Prize, MRS Medal, Scientific American 50 recognition in 2006, RPI Senior Research Award, the Burton Award from the Microscopic Society of America, and the Hadfield Medal for the Outstanding Metallurgist in India. He is on the advisory editorial board of several material science and nanotechnology journals, and on the boards of several nanotech companies. And that's how he is a well-known figure all over the world in the area of nanotubes and also in 2D materials. I think he has started some time ago to work in the area of graphene. And am I right, Sachin?
Yes.
Yeah. Okay. So without taking much time, I would now request Professor Ajayan to give his talk, and this will be followed by some discussion at the end for maybe half an hour or so. Professor Ajayan.
Okay, let me share my screen. Why am I not able to share? Not sure why I can't share my screen.
Is there anything that needs to be done from our end? Today, I had some difficulty in signing in.
I mean, the teams keep changing their...
Yeah. So Microsoft Teams was saying which account do you want to use, your personal account or the institute account? And I say, then it asks for password. Then I gave the password, still it was not opening. Luckily, when I went back, Yeah.
On the top right hand corner, you'll be seeing one arrow pointing up.
Yeah. I'm trying to use that actually. So
if you hit that arrow, it should be able to share
yeah, I
your
mean
screen.
normally it does, but today I don't know what's
It's not
going on.
happening. Okay.
No files available, it's telling me.
Your file needs to be opened onto the screen. It should be available on the screen itself.
Presentation should be on the screen, and then you.
Yeah, you have to open the presentation. Then only it will be able to recognize which one.
Yeah, I do. No. Sorry about that. I mean, I've never had this problem before.
I think there will be some arrow for sharing above.
Yeah.
And if you click on that, then at bottom some desktop screen will come.
Yeah.
So once you hit that desktop screen, your computer is shared. Then you can open your file or whatever you will be opening, that will be available. Yeah, it has come.
Now
it's coming now?
Yeah, it has come.
Oh, okay.
Yeah, it has come now.
That's strange because I don't see it.
Now it is
can
not.
You see it or?
It has come and gone again.
Oh.
Yeah.
Now it is there.
Yeah.
Yes.
Now you can see it?
Yeah.
Oh, okay. All right. So I think the problem is that I cannot be both on the screen and the share screen. So I'll just use this as long as you can see and hear me.
Yeah.
Okay. All right. Sorry about this glitch. Thank you, GBSs, for the nice introduction. It's always an honor to be a part of anything that IIT BHU does because I'm an alum of IIT BHU and I've had wonderful time and memories. And I always think about the times that I spent at IIT BHU. And, especially people like GBSs, I still remember some of the classes that I took from him. Those lays the foundation of, the strong background in science and material science that we all get. So I think, I really savor those times and memories, and I'm always think that where I am at the moment is certainly because of what I learned at IIT BHU. And again, I think when I was there, I don't remember that there was this function called Anveshan. I still remember the Kashi Yatra. I'm not sure if it is still there, which was at the IIT level. But it's great to have such programs and such events that allows you to, bring in people from outside and talk about broad range of things. In fact, I really like that word Anveshan. That's exactly what we do. Explore things. And over the last 25 years, what our group has done is to explore nanomaterials and how they could be built into structures that would be useful in the end. And today's talk, I'm going to be talking broadly about this whole concept of nanoengineering and what are the opportunities and challenges that we face when you think about nanoengineering. Of course, there are this area is huge, and there's lots and lots of work all over the place. So what I will talk about, of course, is based on some of the experiments and experiences we have had over the years. So again, thank you, and this opportunity is wonderful to talk to folks at IIT BHU. Now let me start with a quote, essentially that we all know that the new generation changing the world and who are having the biggest influence on society. Now, coming to nanotechnology, of course, we all know that it's based on a length scale, and today it's already a reality. Many of the semiconductor industry is already working below the 20 nanometer node scale, and the structures are getting very, very small, probably much more difficult to control. There is issues like intrinsic variability of these structures as you build them. And it's fascinating to see how this whole field has evolved and how, where we are in terms of understanding some of these structures, controlling some of these structures. And I think our future technologies will be essentially impacted by the nanotechnology invasion into many, many of the areas, not just one. And again, there's been huge amounts of investment in this area. Countries like the US and Europe has enormously poured in money over the last 2 decades. And if you look at the overall broader picture, you can see that things have gone from the building blocks level to the complex platforms to ultimately in the next decade you're going to see this technology divergence. The impact of nanotechnology in many of the technologies you're going to see in the next decade. That's expectation. And I know that India has also had a pretty big investment in nano initiative, and that has really helped many places in institutions in India to build on our strength. Now, going back in time, nano has been around. It's not that people came up with this type of technology suddenly. Of course, the clear understanding has been reasonably new. But years ago, people were trying to make nanostructures in whatever way possible without perhaps knowing it. Grinding organic compounds with some kind of solvents and then creating nanoparticles that are embedded in different matrices. So you can see artifacts like stained glass windows and beautiful artifacts in museums that essentially have already nanoparticles embedded in them. And you change the colors of these by grinding it more, perhaps using the plasmonic effects and the colors that come out of these nanoparticles. They were able to really manifest some of the outcomes of nanotechnology even in the early days. And of course, nature has played well with nanotechnology, nanoengineering. This is a perfect example of how mechanical properties could be enhanced and amplified by creating the nano-engineered structures. So this particular structure is essentially made of calcium carbonate, which is a very brittle material, but by packaging it into nanoscale platelets and then putting very thin layers of organic glue, which is proteins in nature, they have been able to create this amazingly tough material. And it's a marvel of nanotechnology that nature has created such materials. And we always try to emulate some of these approaches that nature has taken. And this is kind of this brick and mortar type of arrangement that you can see in the microstructure if you go closer. Of course, the long-term goal of nanotechnology is to be able to manipulate and control every atom in the structure, to create new systems, to create systems that have emerging properties like quantum behavior, Again, this is kind of a poster child of that type of an approach from IBM, showing that you can essentially play around and push around atoms into specific architectures that would give you amazing properties and physics. And again, the long-term idea of building structures from bottom up is the essence of nanotechnology. And that's where my talk is going to be mostly focusing on, we can make these nano scale building blocks. How do you really manipulate and create some larger structures, and what are the essential difficulties in doing that, particularly related to interfaces and so on. And I will give you a few examples, all the way starting from the carbon nanotube material that my career started with, and then go into the 2D materials in more detail, which is more recent, that has been going on in our group and in the world at large. Now, let me start with the carbon-based material. Well, since the 1990s, early 1990s, or maybe even late 1980s, people have been looking at the potential of coaxing carbon atoms into various beautiful structures at the nanoscale. And the first major discovery came as a discovery of fullerenes, which happened at Rice University. And the Nobel Prize in Chemistry was awarded to this beautiful molecule called the carbon-60, or the fullerene. And that was really, in some sense, the beginning of nanotechnology, because it captured the imagination of a lot of people, particularly from the point of view that at the nanoscale, you could play around with the structure, and small changes in the structure can have significant impact in the properties. So this was kind of, although it was discovered serendipitously, the beginning of this whole area, and thinking ahead, people were able to really go around and look at other materials and other compositions and figure out how such beautiful structures can be built at the nanoscale with amazing properties. And an extension of that came as the nanotubes. Essentially, it's also the sp2 hybridized carbon. But this idea that chirality in a tube or in the lattice of a small tube that you can build from graphitic carbon, introduces some new properties like semiconducting behavior in nanotubes, really got everybody excited. Because that, for the first time, it was shown that carbon, which is typically a metallic material, semi-metal, could be made into a semiconductor by simply twisting its planar lattice. So that was a remarkable, discovery that Professor Jima made in the early 90s. And again, it contributed to a large number of works in the 90s and later 2000s to suggest the potential use of carbon in semiconductor technology, perhaps replacing silicon one day. And then again, in the late 2000s, there was significant work on identifying these atomically thin layers of carbon called graphene. Of course, we all know that the Manchester group essentially started this using a Scotch tape peeling method of a single layer and exploring the electronic properties of that layer, suggesting that these type of atomically thin materials could be stable and they could provide some real opportunity for building semiconductor technologies or electronic devices. And then, of course, there was a large number of materials that came in suggesting that graphene, the idea of this atomically thin material like graphene, could be extended to other compositions, both single component or multi-component systems, where you can have all the way from insulating behavior to semiconducting to even superconducting behavior. So now today we have a huge family of material systems that has all kinds of compositions, but also electronic properties that range from metallic to insulating. And of course, along the way, the imagination takes the better part of us in many ways, and people like Richard Smalley was influential in bringing people's attention to the impact of nanotechnology. And, he was a very illustrious and imaginative person who was at Rice. He passed away many years ago. he had a huge impact in nanotechnology, and he would say things like, the idea of building a very large fiber from nanotube so that you can actually use it as a space elevator. So all those kind of imaginative ideas really had a huge impact on how this field evolved. And it took a long time to actually get to a point where we could even say that you can spin fibers from carbon nanotubes, which are very, very useful. So, actually, some work that this is some work that has been part of Rice University. My colleague Matteo, who has been able to spin nanotube fiber that shows significantly improved properties of carbon-based fibers. So again, I think this is the pretext of my talk, which suggests that from the ideas and from the imagination that people had in the early days of nanotechnology to actual implementation of things like building fibers or creating larger structures, what are the challenges that we face? And that's essentially the essence of my talk. So let me pick up a few ideas and then give you some examples. One of the main things about nanotechnology is its size. Of course, the elements are very, very small. And the question is, how do you really build interconnected structures, larger structures, mesoscale to larger scale from these building blocks? And one of the things that people use very heavily is the question of assembly. How do you really put these pieces together to make larger systems? And in many ways, nanotechnology is like a Lego game where the pieces are there. We understand how these single pieces behave. But what happens when you start to put these things together? How does the interface work? And how does the individual building block properties scale as you build larger systems? So we worked quite a lot in this assembly of nanomaterials early on. Here is an interesting example, a paper published in 2000s. I think those days, GVSS was visiting us at RPI, and we were heavily looking at assembling nanotubes on substrates. And what you're seeing is an aligned array of nanotubes over a quartz substrate. And essentially, this is not a three-dimensional structure, but it's more like a film of nanotubes that has a reasonable orientation, a vertical orientation with respect to the substrate. But one thing you notice is that as you look more carefully at the distribution of these nanotubes that are part of this film, there is a huge distribution. There's a pretty large distribution in terms of diameter, in terms of chirality, in terms of structure. So it's not really a very uniform structure. It's actually a mixture of various types of nanotubes, which means various types of electronic structure. So that's kind of the simplest way you can imagine a system which can be made from assembly of a large number of nanomaterials. It looks at a larger scale pretty uniform and reasonable alignment, but as you go closer, you see this variation in particle size and structure and so on. In many ways, it's a little bit like the systems that nature builds. If you look closely at these bottom-up manufactured structures in nature, like the shell that I showed you, if you look closer and closer, there is going to be this intrinsic variability in terms of the platelet size, in terms of the thicknesses, and so on and so forth. But overall, the system has very interesting properties, and it behaves collectively quite well. And this is the same problem we see as you assemble things from bottom up, and you are seeing this intrinsic variability in dimensions and structure. That being said, one could think about interesting applications of these structures. One of the things that we looked at was the possibility of using these aligned nanotube architectures as a gecko-like tape, which has got strong adhesion using van der Waals forces. And again, there's been a large amount of work done in this area to mimic, things like gecko feet with high reversible adhesive properties. And we were one of the earliest to show that this is indeed possible by an aligned array of nanotube structures. Also, this type of alignment gives you other, properties to explore. Light absorption is one of them. These kind of aligned materials were shown to be the darkest material. In fact, this came into the Guinness Book of World Records. By creating these very long aligned nanotubes, we were able to show that the absorption of light is quite remarkable compared to any other materials that has been shown before. But the real holy grail in nanotechnology is, especially as you build these from bottom up, is how do you really control the manufacturing and the three-dimensional building of these type of structures from the building blocks. For example, the question is, can you realistically think about creating these type of architectures that are periodic, that have very controlled, interconnections, and this is proven to be very, very difficult, at least until now. If you look at simply carbon-based materials, there are lots of predictions on the possibility of creating very, very well-designed architectures. And these type of structures that has been imagined through theory shows remarkable properties. Some of them are extremely conducting, some of them are semiconducting, depending on the way it is built. And no one has been able to really replicate this at the nanoscale because of the difficulty in the manufacturing processes. I mean, that being said, you can think about creating such architectures at a larger scale. These days, 3D printing or additive manufacturing has become part and parcel to material science. And people have shown that such architectures can be built and printed at a larger scale, in the micron scale where 3D printing is able to do. And they show very, very interesting mechanical behavior. And, again, we are trying to do this with polymers and metals and so on. So it is possible. These type of beautiful geometries and complexities can be created by printing. But the question is, how far can you go in terms of resolution and dimensions? The ultimate goal will be to create structures like this by printing all the way to the nanoscale, and then we can really explore the predictions that was shown by many theoreticians. There is another possible way of creating three-dimensional structures, and that's by playing around with the potential of creating defects in these materials as you grow them. So one of the things that we did in the past was to introduce some dopants like boron into the carbon growth process. And those creates a lot of junctions and bends and so on, ultimately creating these 3D material, which is all based on carbons. Of course, these are essentially porous carbon materials built from nanotubes that are interconnected, and these interconnections are created because of the defects that are introduced when you introduce elements like boron into the process. And we have done a lot of work in trying to explore these individual junctions between the nanotubes, and it's fascinating to see that the mechanical properties of these junctions, electrical properties of these junctions are different depending on how these junctions are created, the dimensions and the geometries. So ultimately, you can think of building these type of porous 3D structures from these building blocks like carbon nanotubes or graphene. This particular image shows the 3D constructs from graphene, and they show some remarkable properties, especially we were looking at thermoelasticity. So structures made from these graphene-like material in 3D shows thermoelastic behavior or elastic behavior at very, very low temperature, all the way to cryogenic temperatures to a very high temperature, about 1,000 degrees or so. So by combining the right kind of nanomaterials and the right kind of engineering, we can build structures that are really superior in properties compared to most of the existing materials today. Now, yet another important aspect of nanotechnology is the question about interfaces and how do you modify and control these interfaces. This is very important because the structures are small in dimension. So as you are building up, you are going to see a huge number of interfaces. And the volume of interfaces is significant, almost as high as the material volume itself. So the way you engineer the interface will have a huge impact on the ultimate behavior of these three-dimensional structures. And the interfaces can be created in different ways. One of the simplest things to do will be to change the chemistries of the surfaces of these two-dimensional or one-dimensional material. People have done a lot of work in chemical modification of these graphene-like materials, and then even finding the right kind of chemistries can lead to some very fascinating devices. This is an example of an experiment we did where we took graphene oxide, which is oxidized graphene, and then reduced it partially to reduce graphene oxide, which is more electrically conducting. And the graphene oxide being insulating and ionically conducting, one could build the supercapacitor-like devices by simple laser patterning. So by understanding the chemistry of the surfaces, one can create very, very interesting devices from these type of materials. The other possibility is to actually create cross-linking. And again, this is a very interesting experiment where we took these building blocks with different surface functionalities and then connected them either through mechanical force or through laser radiation, and we were able to actually create reactions between the functional groups that are attached to different building blocks. And by using that, you can get different types of carbons by introducing these type of interconnections. Now, many of these chemical changes at the interface is done by breaking bonds, so the topology of the system can change by doing that. There is another option where you don't really touch the topology. Well, let's say you take 2D materials, and without really breaking bonds, you can also change the surface chemistry by creating these complexation reactions. Things like acid-base or Lewis acid-base kind of reactions that locally can change the electronic properties and create modification of surface layers and interfaces. Or you can think about intercalation. Many times the 2D materials are layered systems, so you can introduce atoms in between these layers, and that also would change the electronic properties quite significantly. Of course, not every material or layered material can be intercalated with all the elements because of the size of the galleries that it presents. But there are a lot of work that is in literature that shows what can be intercalated and what cannot be. And you can tune the overall electronic properties of these materials or chemical properties of these materials through intercalation. When you go to larger and larger systems like composites, the problem becomes quite severe on how you can modify these interfaces so that you can tailor mechanical behavior or electrical behavior. And again, we have done quite a lot of work in understanding how these interfaces can be modified using chemical modifications. Again, the interface really makes a big difference on the overall properties. If you really don't make these proper connections at the interface between the matrix and the nanostructure that is embedded, you can have a lot of mobility at that interface, the frictional sliding, for example. And this is not always, a bad property, because you can think about using advantage of these weak interface and create materials that could be very useful for damping purposes, vibrational damping, acoustic damping. So there are some potential of also utilization of these weak interfaces. Now, the reason why nanocomposites, the interfaces are so impacting is because, as I said, the large volume of these interfaces and how this huge interface volume can be changed by changing the way these are engineered. And a perfect example of something like this is some experiment we did with nanotube and polymers a while ago. And what we saw was that under compressive loading, dynamic compressive loading, we could see that the material actually self-stiffens, because during this high strain loading, the interface keeps changing continuously. And that's really, very, very unique, because self-stiffening materials would be very useful for many technologies. So using this idea of large interface volume in nanocomposites, one could play around and see what kind of properties can be controlled and what kind of new emerging behavior can be introduced. I'm just assuming that everybody's hearing me, right? You can all hear me and see the slides, right?
Yes.
Yeah.
Yes.
Oh,
Yes.
okay.
Yes. Very good.
Yes.
I don't want to just talk without really getting a feedback. So let me get to the next idea in the whole area of nano engineering, and that is the design of building blocks itself. Of course, most of the previous slides and ideas that I mentioned was specifically on graphene or nanotube, but there's no limitation to the kind of complex building blocks that you can build either. For example, you can create very controlled hybrid nanostructures using templating process. This is something that we have done quite a few years ago. We were able to create these beautiful nanowires with metal and carbon. And obviously, because they have different chemical properties, these type of hybrid structures are almost amphiphilic. So in this particular case, gold can be hydrophilic and carbon can be hydrophobic. So even from a very simple perspective, such hybrid structures can be multifunctional. And here is an interesting example of using something like that. So what we did was to demonstrate that these hybrid nanostructures could assemble in very different ways depending on the environment that it is in. So in some cases, you can make it to assemble with all the gold side facing out, or you can do the reverse way by creating the carbon on the other side. By using this this amphiphilic character of these nanowires. And this leads to this whole concept of reconfigurable assembly. And the question is really, and actually there's a lot of work coming out these days, and there's a significant interest in the, in funding agencies and so on, to create what they call the 4D approach. So, you can create a 3D material from these building blocks and create conditions where the structure can assemble and deassemble and reassemble and so on, to create this 4D kind of material, things that can be tailored or dynamically reconfigured. And that's really the future of nanotechnology in some sense, where stimulus can be used to kind of assemble, deassemble, reassemble, and so on. And in fact, we have built some of these nanostructures, hybrid nanostructures, that could be essentially a device in itself. So by appropriate model systems that can be templated, one could create, for example, an entire battery on a nanowire, and they seem to perform reasonably well and cycle reasonably well. So the idea has been around for a while. People were actually building solar cells in a nanowire, batteries in a nanowire. So in the long run, if we think about a totally deconvoluted system where the energy is decentralized, one could certainly think of having every sensor powered by its own energy source, like a nanowire battery or so on. So there's a long-term perspective, and I think engineering of nano materials in the right format would allow you to do things like this. This is actually some work taken from our friend Pradeep from IIT Chennai. And he has been, of course, looking at a different type of building block, which is a cluster. And by utilizing these ligands, he can also build, and several other groups in the world can now build three-dimensional structures. The beauty of this kind of thing is that the clusters are now size selected, so they are much more uniform, and the periodicity can be controlled by the ligand. But of course, these are essentially influenced by not just the cluster, but also by these ligands that you use. And there are some disadvantages of stability and so on in terms of temperature. But, these kind of approaches kind of give you a glimpse of what the long-term materials from nanotechnology can look like. Large periodic arrays of size-selected nanomaterials would give you very, very well-defined properties. Well, in the last part of my talk, let me come to this 2D atomically thin materials, which I have mentioned a few times. But our focus in the recent years has been trying to understand how these structures can be, again, manipulated. So this is an image showing an MOS2 molybdenum disulfide layer sitting on a silicon step. And what you can see is the essence of what 2D materials might look like, especially when you're starting to think about making devices and so on. So you can see all these small defects that appear, like blisters or wrinkles, and and those are unavoidable, really. And that's essentially the nature of this kind of system. And what is again quite challenging is the fact that such small perturbations in structure can lead to some specific changes in electronic properties. So here is a very specific experiment where you wrap these molybdenum sulfide on pre-patterned substrate and then use a scanning tunnel spectroscopy technique to understand the electronic structure of these molybdenum sulfide surface. And what you see is that at the tips where the stress is concentrated, the electronic structure actually changes and it becomes more metallic. So you can imagine when you're starting to put these 2D layers on substrates to make a device, all these blisters and wrinkles and so on will have an impact because they will locally change the electronic structure. So it goes back to the same problem of this intrinsic variability that you cannot really avoid in nanomaterials and nano-engineered structures because of the strong structure property correlation that exists in these materials. So it's really a fascinating perspective on how you can really build devices from these nanomaterials, but at the same time, you have this difficulty in really controlling every aspect of its structure. But at the same time, these 2D materials have really gotten a lot of attention recent times. And again, Feynman was fascinated by these materials because they had these very anisotropic bonding. The in-plane properties very different from through thickness properties. And he had this idea that what can you do if you take out these layers one by one and then mix them together with some other layers. It's like a deck of cards. You can take a blue and red packs and then just shuffle them together. And what kind of properties would that bring? It's really a fascinating question, especially for a material scientist. This is really amazing what kind of things you can do. And of course, with 2D materials, there's also been a lot of suggestions on new types of devices. There's actually a beautiful work coming from Santa Barbara in collaboration with our group, showing that some tunnel FETs can be made, which shows performance that is really beyond what is possible with typical silicon devices. Particularly, some thermodynamic limits can be broken using these extremely thin channel materials like molybdenum sulfide. Now, the question is really, of course, how to make some of these 2D materials. I already mentioned that the graphene layers were made by simple physical Scotch tape peeling technique in the beginning, and then later using exfoliation. Now, exfoliation has become quite a powerful technique to extract layers from different materials, layered materials, even non-layered material. If you can provide enough energy, you can cleave these different materials along different crystallographic planes. And again, getting to super thin layers could change the overall behavior of these systems. Here is an example of an iron oxide which has been cleaved, and when you've reached very, very thin layers, you can get some new emerging properties like magnetism and so on in these. Of course, exfoliation creates bulk amounts of these 2D layers, but if you want to get more controlled layer growth, you need to do vapor phase deposition or CVD growth. And there are many techniques now that allows you to grow large areas of these 2D materials like molybdenum sulfides or graphene. And we were, in fact, one of the early pioneers in trying to grow these dichalcogenide material from oxide precursors using chalcogenization in the vapor phase. And there are other, again, new techniques that are emerging as well. Some work that we did with a group in China, suggesting that 3D Maxine-like materials could be transformed to 2D structures using interaction with vapor phase gases like hydrogen sulfide. So there are multiple ways of creating these materials, either by vapor phase deposition or by exfoliation techniques. Now, many of these techniques, of course, are nucleation growth problems, and Hello?
Yes,
Can you hear me?
Please go ahead.
Oh, okay.
Yeah, we can.
All right. So I should be done in about 10 minutes. I was saying that CBD growth produces defects, and the defects in some of these 2D materials are also quite interesting. For example, if you look at graphene, which is a really single atomic 2D layer system, it's a hexagonal honeycomb lattice. One would wonder what the grain boundaries and things like would look like. And it seems that these grain boundaries are made from topological defects like the 5-7 membered rings. People call it the stone Wales defect in carbon. And it has been shown that these defects now are really present at these grain boundaries. And even the electron transport through these grain boundaries depend on how exactly the grain boundaries are made from these defects. So there's a lot of detail that could be fascinating in some of these atomically thin materials. And it's the same story with other 2D systems. Of course, something like molybdenum sulfide is not exactly a 2D layer because it has got 3 layers, 1 of metal and 2 of sulfur. A single unit is essentially made of these 3 separate layers. And again, if you look at the grain boundary, you can find these defects like 5-member and 7-membered rings. And they have their own local electronic structure and properties, which people are fascinated about. It's also been proven, and again, this is a challenging area, that having defects can change the overall electronic properties of these materials. And it's not so easy to determine or control the number of defects that are present in these systems. Here is an experiment that is from the Columbia group showing that depending on the defect density in these materials, your electronic structure could be quite different. And they have shown this by photoluminescent spectrum that really an ideal PL spectrum comes from a material that has very few defects, which is kind of understandable. So there is another aspect to this. Again, to get consistent results, you have to go to larger grains or even larger scale single crystal type of material. And many groups have shown that you can grow really large 2D single crystals without grain boundaries under the right conditions. So again, from the growth perspective, there's been a lot of progress, but still one needs to continue to make significant contributions to make materials that are defect-free so that you can really control or engineer these type of materials in the actual devices. Another fascinating aspect of these type of materials is the fact that I mentioned in the beginning, that you can mix and match and build up these stacked structures just like a deck of cards. And this is really very interesting because you can make artificially stacked materials that has not been shown before. So I can think about, let's say, take a graphene layer and a boron nitride layer, which are almost isostructural but very different electronically, and then stack them together and see what these hybrid materials can provide in terms of properties. Now, in addition to just the stacking of layers, especially when you stack layers, there is another interesting aspect that comes into picture, and that is the rotational disorder. So, for example, graphite, you can either stack as banal stacking, which is essentially the real AB stack graphite, or you can have rotationally disordered graphite, which we call turbostatic graphite. And the electronic properties are different in these. So this rotational disorder or twisting or essentially rotation kind of brings in a new aspect to these type of artificially stacked material as you start to do this. Of course, there is another aspect as well, which is related to the phases that exist in many of these 2D materials like transition metal dichalcogenides. Some of them are metallic, some of them are semiconducting. That we call it the 2H phase or the 1T prime phase. And when you stack them together, then you could think about even having metal semiconductor layers stacked together. So there's a lot of interesting possibilities which has not been explored really to that extent, and that leads to the potential of creating very different artificial materials using this stacking approach. And again, the long-term possibility is, how do I build different types of structures with different properties by these building blocks that are 2D layers. One way to do this is using multiple precursors and using vapor phase deposition. And we have grown many of these hybrid layers together, and they can be formed. For example, molybdenum sulfide and tungsten sulfide are very similar type of material. And using different precursors, you can create these heterostacks. Now, it looks like you can optimize windows in which you can grow these stacked structures that are completely segregated, the composition. Or in many cases, what happens is that within the same layer, you have these contiguous structure with different domains of tungsten sulfide and molybdenum sulfide and these domain boundaries. So you can have these in-plane structures as well because they are isostructural. And again, I don't want to go into details of these characterization methods and all that, but we have found windows of growth process where you can create these preferentially 2H stacked material. Again, that depends on the way these metal atoms sit on top of each other from different layers. Or we can preferentially create materials that have these in-plane structure. And when you say in-plane, these are really very interesting interfaces because they are almost atomically flat interfaces between the tungsten sulfide and molybdenum sulfide. And of course, you can see some atoms that are diffusing into the neighboring domain. But one could essentially think of creating really sharp interfaces in all 2D hybrid materials structures. And of course, in recent times, there's also been this whole area of twistronics coming into picture, where you can take layers of graphene or 2D material and twist them and create this moire kind of patterns. And it looks like if you have the right kind of moire, you can have electron correlations, and you could even think about having properties like superconductivity. It's been very well known that twisted bilayer graphene shows a highly correlated electron system and properties like superconductivity. We can also go to the ternary phase diagrams in some of these materials, which has many phases that are isostructural. For example, the boron-nitrogen-carbon system is very interesting. Boron nitride is an insulator electrically, and carbon is a metal. And there are many other phases that are semiconducting, like BNCs or BC3. But most of the time when you're trying to grow these kind of materials, what you end up with is this segregated domain structure that you're seeing in this image. And we have tried to grow many of these layers. They are highly graphitized layers, but if you look carefully in high-resolution TEMs, you can see that the domains of BN and graphene are segregated or separated in these layers. And we have also done quite a bit of engineering in trying to figure out how you can create particularly sized domains or particular distribution of domains, and that could lead to some very interesting device ideas. For example, if you can stitch together some graphene within the hexagonal boron nitride matrix, you can create these two-dimensional antennas, which are, again, quite fascinating because you can essentially peel off this layer and put it on top of any other substrate. And you can make many patterns within the 2D. So this is kind of the ultimate engineering of nanoscale engineering you can do, and this being a 2D platform. Well, hexagonal boron nitride itself is a very fascinating material. It's similar to graphene, but it's very robust in terms of oxidation resistance. We have shown that these layers, a few layer thick BN, can be extremely good in oxidation resistance at very, very high temperatures. Recently, we have also shown that if you can coat these boron nitride on some of these steel meshes, which are used in desalination membranes, they can be protective in terms of the metal not being oxidized, and that allows industrial performance to be much better. It's actually a very recent paper that shows that BN can be very useful. There is another potential of building these lateral heterostructures, and that is with the different phases that I mentioned. So in the case of BN graphene, there were different compositions, and electronically they were quite different. In these type of materials like molybdenum telluride, you can have this 2H and 1T prime phase, where the electronic properties are different, but the composition is the same. So if I try to grow molybdenum telluride, typically, what you end up with is these 2H phase and the 1T prime phase that are merged together within a single unit thickness. And 2H is semiconducting and 1T prime is a metallic phase. They're slightly different in structure, but they're pretty close in terms of lattice parameter and so on. And there's been a lot of work in literature appearing in very good journals suggesting that you can do this phase patterning. For example, by using radiation, you can convert the 2H phase into 1T prime phase by this structural transformation. And of course, that is very tedious in some sense. So one approach that we recently took to make these large-scale periodic 1T prime 2H phases in a periodic fashion is to dope this material with another element. So it looks like if you dope molybdenum telluride with tungsten, you essentially stabilize the metallic phase. So what you're seeing here is actually an array of 1T prime lines that are embedded within the 2H phase by using this doping approach. And that allows you to create large areas of these periodic structures that is alternating 1T prime and 2H phase of molybdenum telluride. Now, doping, of course, is also a possibility on large areas of these 2D layers. And we have, again, worked on doping with elements that are similar. For example, you can dope molybdenum sulfide with selenium or tellurium. You can dope molybdenum sulfide with tungsten. And that can lead to pretty good alloys of these elements, 3-component or even higher component. And that changes the electronic structure. And you can tailor the electronic properties by changing the concentration of the dopants. And it's also been seen that going from 2-component to multi-component, you get a higher band gap tunability. And again, we have done quite a bit of these alloying of various types of elements and going to quaternary systems. And here is actually a nice image that shows these alloys in 2D of molybdenum, tungsten, sulfur, selenium. And this is actually a energy filtered image taken by the Oak Ridge group from a sample that we created, showing a very good distribution of these elements in this 2D layer. And we are now pursuing properties of some of these materials, for example, catalysis and electronic property of these layers. And these 2D materials can also be broken down into smaller dimensions, like quantum dots. And we have started to do this for graphene and other types of 2D materials. We recently published some work related to this cryo-initiated liquid phase creation of 2D quantum dots. And again, essentially, we can create quantum dots from pretty much all of these 2D materials. I should say quantum disks rather than quantum dots, because they are 2D. And they seem to have some very promising properties, for example, catalysis. So the nitrogen-doped graphene quantum disks or quantum dots were useful in CO2 reduction as a catalyst. And of course, CO2 reduction is an important technology that is coming out now. And the only real good catalyst is based on copper, but metal catalysts are always problematic because of stability and so on. And the carbon-based catalyst seems to hold some promise in this area as well. So let me kind of end here. Essentially, what I showed is take a lot of examples from various stages of our work in the last 2 decades or so, showing that you can not only make some of these building blocks, but also you can create some engineered structures using these building blocks. And many times, you are kind of limited by the properties of these interfaces. And the question really for the future is how well can you control and create these nano-engineered materials? You can be very creative in making a lot of different structures, but the real question is, can you design and build using nano-engineering some of these architectures that has been predicted to be very interesting? And I think the future of nanotechnology will depend on how well you can do this, what kind of tools are available, how good the tools get in the future. For example, lithography tools can go to almost a couple of nanometers now. And the question is, can you push that? And if you can push that to even smaller scales, the top-down approach can be still very valuable. Otherwise, we'll have to resort to these assembly techniques and bottom-up approaches to build these beautiful architectures. And of course, the future is going to be, technology-based, and you're going to see a lot of embedded sensors and interactive devices. Of course, the Internet of Things is becoming very popular, and many of these, platforms are going to have nano devices, nano sensors. It's already there. I mean, most of the new chips are all going to contain nanoscale devices and structures. But I think you're going to see more and more of this IoT type of approach of really making everything more interactive, more smart, intelligent, and I think that's the way life is going to be in the future, and it's pretty much driven by the advances in technologies. So a lot of people to thank, and my group is very, very interesting from the perspective of a global composition. People from all over the world come together and work together to create advances in basic technologies and sciences. So once again, let me thank you for this opportunity to talk to you about some of the work that we have done over the years, and at least to give you a glimpse of what kind of beautiful structures we can create using nanoscale building blocks, and that's been essentially a summary of many things that we have done over the years. Thank you.
Thank you, Ajayan, for the highly illuminating talk. You had summarized, in summary, I'm just saying that you started with building blocks in 3D structures to interfaces problems, and then design of how the building blocks can be done. And also, at the end, you had come to the 2D atomistically thin structures and hybrid layers. One thing which also you mentioned, the difficulties associated with these interfaces in such type of designs, and the difficulties in reaching the end goal without any defects. So that's where I was also feeling that these defects which you mentioned on the surface, bumps that were there, perhaps cannot be avoided. It reminds me of the difficulty of growing single crystals. Truly single crystals where perfect alignment of the whole lattice is present is quite an engineering challenge. And maybe same thing you are finding it in this one. So before I open the talk for discussion, you referred to Kashi Yatra. It is very much there. It takes place, of course, with slightly modified versions of it, but it is still there. And Anveshan, it was not there earlier because this is the 9th edition of Anveshan, started only 9 years ago. So
yeah. Thank you, GVS. I think the comment that you made is very much valid. Particularly the defects. Obviously, we all know thermodynamically you cannot really avoid defects, But the question is really, when you go to nanoscale, for example, a nanotube or something like that, can you reduce it to, to a very small limit? Because end of the day, what people are trying to do, I didn't mention too much about defect engineering. There's a lot of quantum technologies that are coming in based on this idea that you can engineer individual defects in lattices. So even though we may not be able to entirely eliminate defects, if you can actually go to the lower limits, that would certainly help. And perhaps creating nanostructures is one of those ways of doing it.
Yeah, on a philosophical level, I would only say that just like nature, we should also be ready to accept these defects and then take them along with the material. Maybe that is the only ultimate
that may be another approach to do this. I mean, or maybe intentionally create defects, right? Yeah. I mean, that's another possibility.
Yeah. Okay. Friends, now the talk is open for discussion, and I request and encourage the young participants to take this opportunity to discuss their ideas or the doubts that they have in their mind with Professor Ajayan.
So the audience are mostly undergraduate students?
Yeah, faculty from some institutes and also undergraduates of the department and outside the department.
Some graduate students are also there.
Mm-hmm. Yeah.
So, Professor Sastry.
Yep. Yeah, please go ahead.
If there are no other kind of participants coming forward, if I can start some discussion.
Sure.
Okay?
Yeah, sure. Please go ahead.
Professor Ajayan, it was a very wonderful talk and you have covered too many things. I think it requires several lectures for many of the students to grasp. But nevertheless, it has given a good flavor. But I will ask a specific question, but the one general questions for the benefit of the students. You mentioned that carbon behaves like a metal, that means the metallic behavior. And many of our students, they know that carbon as a diamond is insulated. And also the semiconductor, various forms, the nanotube and all. Can you briefly mention and elaborate just before the students and also many of our non-specialists that how and when carbon behaves like insulator, semiconductor and metal? These are my general questions. After that, I will come back to the specific questions of my own interest.
Yeah, sure. I mean, it's a textbook material, I suppose. Essentially, carbon has various types of hybridization, depending on how the 4 electrons in the valence band is hybridizing, whether it is an sp2, which has 3 sigma bonds, and the pi bond that is kind of delocalized, it behaves more like a metal in plane. And of course, if all the bonds are already covalently taken, then it's essentially an sp3 hybridization, which makes it an insulating, like a diamond, right? So again, solid carbons, these 2 forms, the graphitic, which is sp2 hybridized, and the diamond-like, which is sp3 hybridized carbons, end up as 2 ends of the spectrum, one being more metallic and one is very insulating. It simply depends on whether electrons are available to be delocalized, which is the case in sp2 and not the case in sp3. So that was the traditional view of the carbons, solid forms of carbons. And now the real innovation came when the nanotubes and similar type of materials were discovered, and then they realized that this electronic structure could be kind of tailored by going to very small dimensions, or maybe creating lattices that are slightly twisted, like a chirality issue, or maybe this whole idea of electron correlation when you have two layers that are twisted. So some of it is, of course, is probably beyond the scope of what the students can understand, but certainly, I think when you go to smaller scale, the impact of both the dimension and lattice reorientation can create changes in the band structure that actually can potentially move, materials like carbon from a zero band gap, semi-metal to more semiconducting. It is not really that easy, actually. I mean, one of the reasons why graphene is still not a great semiconducting material is that you can't really move the band gap that much, right? You can't. A few MeVs maybe. And that's one of the reasons why people have shifted to these other 2D materials, which are intrinsically semiconducting. But the nanotube is a slightly different case because it's a one-dimensional structure, and you have a higher, better chance of moving the band gaps to larger values compared to graphene.
But do you think that the free electron theory, like a metallic bond, will be able to experience in the carbon structure?
I would think so. Yeah. I mean, I think the basic, the basic electron structure, electronic configuration is similar to metallic systems, I suppose, in graphene.
Okay. So the carbon, whether it is metal or non-metal, we have to say that depends on the situation.
Yeah. I think in the long run, there is a lot of interest in trying to see if the sp2 and the sp3 carbons can be mixed together. And, some of those architectures that I showed in the beginning, there's a lot of, carbon is a fascinating material. You can really, because it bonds in different ways, specific ways like sp3, sp2. You can actually create carbons that are magnetic, for example, theoretically at least. By creating the right kind of bonding distribution, and I think some of those things are coming. The people are now fascinated by how you can tailor carbons at the bonding wise.
Okay, thank you, Professor Lele. Professor Sastry, can I complete my questions, or I will come back again?
If there are no others waiting, then maybe you can.
Okay. You have introduced one particular phenomena, the dynamic self-stiffening. Can we expect that this property, suppose if I put carbon nanotube in the metal matrix composite, will that be possible phenomena in this kind of situation?
That's an interesting question. I mean, again, I suppose, I think the fact that we found this phenomena in the soft polymer system is, first of all, we could strain it to very high strains. And, essentially in order to change the mechanical behavior or the interfacial behavior, it has to be somehow reconfigured. And I think at low strains, we didn't notice it much. In the case of metals, I don't know if you can go to high strains. Maybe some metals you can, or maybe you can use.
What happened? There is a failure of this one.
Hello.
Yeah, the voice has got lost.
Yeah, but our communication is okay, no?
Yeah. Ajayan, are you able to hear us?
I think something got disconnected.
Yeah.
Jashudia, you are able to hear us?
He got disconnected. He's there. He's there now.
I can hear you.
Okay.
Yeah, but Ajayan got disconnected.
No, he's there, sir.
No, he's there, picture, but voice.
My link is there.
Yeah.
Somehow his computer might be hanging. That's
Yes.
Yeah.
But he may not be realizing, I think. He might be talking.
Ajayan.
Yeah.
Ajayan.
now back.
Are you
Well,
back?
hello?
Are you able to hear us?
Hello?
Hello?
Yeah, Ajayan, we are
Got lost
unable
for
to.
some time.
Yeah, I don't know what happened.
Okay.
I think it said there was some glitch in the program or something. I mean,
Okay.
Yeah.
So
Yeah.
now, yeah, continue.
Okay.
Here.
yeah. So
Yeah.
I think it's a very interesting question. We haven't really explored it to that extent, but I'm pretty sure that if you could, create the right interface, perhaps with the right kind of metal carbon bonds, we might be able to see some changes. I mean, I don't think it will be as demonstrative as the polymer system because you could strain pretty, heavily.
Okay.
But maybe there are some other, interconnections that one could introduce that would have an impact.
Okay.
But it's, it's a very
Yeah.
curious question.
So my last question is that the exfoliation, what you were trying to show that to get a two-dimensional layer by cleavage plane or even not, whether the cleavage is there or not. My curiosity is that do you think that amorphous material where the cleavage doesn't exist, you think it should be possible to get a layer of amorphous kind of system?
Yeah, so we have been, fascinated by this idea that maybe you could make a 2D glass at some point. I think there's some, there are some demonstrations, but not very convincing. Exfoliation, it might be difficult. I mean, I have a feeling that to get a larger, two-dimensional surface area from such brittle material without any cleavage planes, as you said, in my opinion, could be quite challenging. But maybe physical exfoliation might be the right way to do it. I mean, I suppose, I don't know if you're talking about real glass or maybe some metallic glasses kind of material. I mean, one thing that we did recently was that if you have a metal that can have a lower melting temperature, you could essentially surface melt a layer and pick that up. So it might be possible, even in the case of metallic glasses, that you might have, you could create a thin surface molten layer and essentially pick that up and create a 2D, amorphous material. But just high intensity exfoliation, it might actually just break up into small particles.
The layer, 2D layer, atomic layer, once it is of any particular type, maybe it is difficult to break the bonds there. And so some atomic order will always be present once you go to one atomic layer to the material, perhaps.
Yeah,
so
I mean, the basic question we were kind of thinking about is, can you actually have a 2D glass, from a theory point of view?
Yes.
Right, because
you are aware of this vitreous carbon. Vitreous carbon it's amorphous, and then it is very much available. So in one sense, that is there.
Yeah.
Dr. Arup Das.
Thank you.
Santanu Das has been waiting.
So, Professor Ajayan, is a mesmerizing talk. So, thank you so much for giving us such a beautiful overview. And I have a quick question regarding your alloying of 2D materials that is sold, and moly, tungsten, sulfur, selenium. So, how much you think it could be homogeneous? Like it's been phase separated, or it's just you think?
That's a very good question. But by the way, I mean, maybe it's a good thing to introduce yourself when you ask. Are you from BHU or?
Yeah, I am from Department of Ceramic Engineering at BHU. I met you in a couple of conferences in MRS, and I did my PhD from Hong Bong's group in FIU, Floyd Anderson University.
I see. Right. Yeah, very nice. So it's a very interesting question, right? So we did a lot of experiments based on this alloys and this possibility of segregation. In fact, most of the work was done by my postdoc, Chandrasekhar Tiwari, who is actually a faculty in IIT Kharagpur now. So it clearly, undergoes phase separation as a function of temperature or as a function of certain elements that you add, especially if it is not isomorphous. You can have
making this.
Yeah, so I mean, this particular system, like the moly, tungsten, sulfur, selenium, when we made it by vapor phase, they looked very uniform, but we were able to show that you can, in fact, force it to separate as you increase temperature, for example.
That's correct. So my question is very, very is there any real motivation of allowing this kind of things when things making more complicated? Because I agree with your the topic, which is very interesting of stacking of MOS2, WS2, and a lot of other things, because interface matters. While you are having this electronic properties.
Right. So the motivation for alloying was essentially to look at how the electronic structure is changing and what kind of band gap tunability you can have. And there are applications like catalysis that that has a lot of potential. I mean, if you look at molybdenum sulfide catalyst that is used in chemical industry quite regularly, they actually add elements like nickel and tungsten to a smaller amount because the pure MOS2 is not very catalytic. So I think there is a lot of potential development or design of catalysts if you go to the 3-component or maybe even higher component systems. And again, our main interest was mostly academic, and we wanted to see how the phase stabilities happen when you have multiple components and so on. But it looks like there is a strong application interest as well in these type of alloys.
Thank you so much. It was really, really exciting talk. Actually.
Thank you.
We enjoyed a lot. Actually, thank you so much.
So, yeah. Are there any?
GVS, I have maybe another 10 minutes. I have to go to some other place after 10 minutes.
Okay. Yeah.
But yeah.
Are there any others who would like to discuss?
I mean, you are most welcome to also email me. I mean, my email is ajayan@rice.edu, and keep in touch for sure.
So, shall we come to conclusion, Professor Basu?
Yeah. I think yes. I think you can conclude. It looks like there is no other question.
Yeah. So, friends, I'm sure you would all agree with me that it has been a highly illuminating talk. Professor Ajayan, as I know him from his student days, is a versatile personality. Many of you may not be knowing. He even used to write poetry, and I still have that copy with me. And very enjoyable. You never see him serious at any time, although he is extremely busy. He is gifted with that natural curiosity, and then that is what drives scientists and explore all possibilities, because there are infinite number of possibilities, and then it only is left to you to explore them. And that's what he has demonstrated. And during my stay, which he mentioned for a brief period at RPI, I used to see that every day there is a new idea, and then it is either covered by some top journal or news channel, including BBC and so on. And he even produced one toothbrush out of carbon nanotubes, and that at that time I was even suggesting to him, why not have nano diamonds attached to that brush so that you can polish metals or glass much efficiently as compared to normal polishing techniques. I think so. Through his work that he has presented very briefly, it is an immense amount of work. He showed us and the youngsters all together what are the possibilities that you can explore, and then many of them are very interesting and also have application in industry. They are not only theoretical curiosities, but many of them can be thought of as a having potential applications, if not immediately, but in near future. So thank you, Ajayan, and then we wish that you visit the department more often, and then and also interact with the students of the department and faculty of the department.
That'll be really wonderful, GVSs. I mean, I'm in fact thinking of spending a little bit of time in India as a sabbatical end of this year. So I will certainly come and visit, and hopefully I'll be able to see many of you in person.
Yeah, I think the department should take that opportunity and immediately write and make arrangement of how he can be invited and spend time. That will be very inspiring for faculty as well as the students.
Thank you very much.
Thank you.
And see you.
Yeah. Okay.
Bye-bye.
Bye.